Welcome to MET 200 Manufacturing Processes and Material. This is Dr. Hamid Isazadeh. In this lecture, we will talk about powder metallurgy. In the book, we have a part 4, particulate processing of metal and ceramic, and but here we mostly focus on the powder metallurgy, and we talk about the characterization of engineering powders and how metallic powders are produced, and what are the process that we use for the powder metallurgy. Powder metallurgy, which is called PM for short, it's a metal processing technology where we can produce parts from metallic powder. This process has two steps. One step is pressing the powder and compressing the powder into desired shape, and it is called green compact, the result of the first step. The next step is sintering, where we use the green compact from the previous step and heat it to a certain temperature. The temperature can be very high near the melting point, but it doesn't melt the powder. The word green means the part is not fully dense, or it is not completely processed yet. We have a series of steps. In the conventional, we have these three steps: blending and mixing the powder. So depending on the application, we have a certain ratio of different powders, and we mix them, and then we make it ready for the next step. So this part is going to be mixing the powders. The next step is compaction, where the powders are placed in the dies like this one, and then we have a punch that pressed these powders with a certain load. The next step will be placing the green part, this part, green part. We place it in the oven, or the not or a furnace, and raise the temperature to a certain point, and the particle will bind together, and then it creates a solid product. And here is the last stage. The part is showing is a hot pick after sintering step. In the first step, we can have blending. Also, we can have mixing of the powders. If we want to have successful result in compaction and sintering step, the powder must be homogenized, and this can be done by blending, and the powder of the same chemistry should be intermingled. The size should be different. If the size are different, then you have a reduction in the porosity. We can mix different material, different powder, different chemistry, and that is called mixing. It's not blending anymore. Compaction, which is the pressing step, is required to form the powder into the required shape. basically what happens, the powder are going to be squeezed together using two opposing punches. Once the powders are squeezed together, we have a green compact, and it is not fully processed yet. It has to go through another step, sintering, and this part is very um, brittle, so it has to be handled with care. This machine is a hydraulic press used for the powder metallurgy. It's um, actually pressing machine, and the pressing step is done with this huge hydraulic press machine. And this picture shows us sintering sequences on a microscopic scale. As you see, we have a point uh, bonding between the particles, and then we have a necking, so that bond becomes larger, and then we have smaller pores between the particles. Then here we have grain boundary between the particles. The PM, or powder metallurgy, is important for a couple reasons. First is that the PM parts can be mass produced, and they can be produced to net shape or near net shape, which can eliminate the need for the machining processes. So if you remove one process, for example, machining, um, you can save a lot of cost. The next advantage is that it has very little waste material. Up to 97% of the powder we use in PM technology can be converted to the final product. And the third step is PM part can be made with a specified level of porosity. So it can be advantages. So we have one part, and we know how much porosity that part has. We can manipulate the level of that porosity, so to produce a porous metal part, where we can use this part for filters and other application. There are other reasons for PM technology. For example, certain metals are difficult to fabricate by other manufacturing processes, like a tungsten filament that we use for incandescent lamp bulb, are made by powder technology. The next advantage is certain alloy combination and cermet made by PM cannot be produced in other uh, method. For example, in the PM we have punch and die. So here is the die, and this is punch. We can add powder in certain, one type of metal powder in a certain ratio at the bottom, and we add another type over there, and we can add a different powder on top of the previous one. So we can change um, the combination. We can have various alloy elements in that die, and then bring this um, punch toward the die to press the part, press this powder. So this comes here and it compresses all the powders and it becomes a green compact and will be ready for the next process, which is heating. When we heat the part, this powder will bind together and can make it the final product. There are other advantages, like this process can be automated to make it more economical. The limitations of this process are listed in this slide. We have high tooling and expensive equipment for this process. The next drawback or the next limitation of this process is that the powders, the metallic powders, are expensive, so because the production of the powder is difficult. You need to make all the powder in the same size. Their shape is important. That's why the powder normally are expensive. And we have problems storing the powders because over time they may degrade, and there are some fire hazard for certain metals. The next problem is the limitation on the part geometry, because the metal powder cannot flow laterally in the die during pressing. So if you have a die like this and the powders are sitting here, and you have a die here, you have the punch up here, and the punch is coming this way, the powder may go in Y direction and in X direction. For example, this is X direction. They do not flow. So that is a problem if you want to make a part, a die, different shape in more complex geometry. If you want to extend the shape of the die and make it larger in this corner, then this powder won't flow in this side of the die to fill that corner. So this becomes a problem. Next problem is the variation in density throughout the part. So it is possible that this area we have high density, and this part of the product we have less density. So that is another different, the difficulty problem associated with the PM. What are the materials that we use in powder metallurgy? Mostly we use iron, steel, aluminum in the PM method. It is possible that we use other metal like a copper, nickel, refractory metal like molybdenum and tungsten. Also, we can use metallic carbide like tungsten carbide in the PM process. This picture shows some of the powder metallurgy parts. As you see, most of them have simple shape. The powder metallurgy method, we use a powder as I mentioned before, and the powder is a particulate solid. And this powder can be metal powder, can be ceramic, but here we are mostly focusing on the metal powders. And there are some features, geometric features for the powders that are important for the process, like particle size or the distribution of them, and what is the particle shape or the internal structure of the particle or the single powder, and what is the surface area of the um, particle. As I mentioned before, one of the geometric feature is particle size, and we have to measure the particle size with different method. One common method is to use a screen mesh, and the screen mesh we can have different size. Here, as you see, if the particle, this is the one screen mesh. If the particle is larger than that, screen mesh size, it won't fit, it won't pass. If it is smaller than that mesh, it will fit, as you see here. And uh, particles are going to be sorted by passing the particle through the series of screens progressively to a smaller mesh size. And the word mesh count means the number of opening per linear inch of a screen. Here one example, if we have number 200, it means that we have 200 opening per linear inch. Next geometric feature is the particle shape, and in the PM we have different shapes. As you see here in this slide, we have a spherical shape, we can have rounded shape for the PM, we can powder with a cylindrical shape, or a spongy, or a circular, flaky, or cubic, or aggregated. There are other features for the engineering powder, such as interparticle friction that we discuss here in this slide. We have flow characteristics, that is another feature, or packing, density, porosity, chemistry, and surface films. In this slide, as you see, we are looking at the friction and powder flow. And the friction between the particles um, normally affects the ability of the powder to flow, and it will affect the pack tightly. And here is we have one method for measuring the friction or the interparticle friction in the powder. If we can have a funnel, a simple funnel, and drop the powder from that funnel into the pile, and then the pile will make an angle, and this angle can be measured, and it is called angle of repose. If you have a larger friction between the powder, um, the angle becomes steep, like that. If the powder has no less friction between each other, it means that you have a smaller angle of repose, or you cannot make the pile very very high, so this distance will be short. If the particle size is small, then we have greater friction and the angle is going to be steeper. So you have a larger angle of repose. The next observation in the interparticle friction is that the shape of particle affects on the angle of repose. If you have a spherical shape, you have a smaller angle of repose or lowest interparticle friction. As we change the shape from a spherical to other shape, the friction between particles normally increases. It goes up like this, and the angle should increase. Sometimes lubricant is added to the powder, which can reduce the friction between the powder, so you will have a better flow during a pressing process. When we want to measure the packing characteristic of the powder, we have to know two measures. One measure is the true density. The density is the true density is the density of true volume of the material. Or another way, the density of the material if the powders were a part of a solid mass. Okay? And the next one is bulk density. This is the density of powders in the loose state after pouring on the flat surface. Because always we have some pores between the particle, the bulk density is going to be smaller than the true density. So this value always is smaller than the true density. Since we know the bulk density and true density, here we can measure the packing factor. And the packing factor is the bulk density divided by true density. And this value depends on the particle shape and the distribution of particle size. This value is going to be between 0.5 and 0.7. It's always less than 1 because it's not fully dense. And if you have various sizes in the part, for example, you have some small smaller powder with the larger powder, what happens, the smaller powder can fit into the spaces between the larger ones. So this can increase your packing factor. Another way to increase the packing factor is to vibrate the powder. If you vibrate the powders in the die, it causes them to settle more tightly. The next method to increase a packing factor is that we can apply pressure during compaction, and that pressure should be larger. If you apply larger pressure, that will increase the packing factor. Here in this slide, we talk about production of metallic powders. In general, um, different company make the metallic powders. So the producers of metallic powders are not the same company that make the um, powder metallurgy parts. We can make powder from any metal. It is possible. And there are various methods to make powder. One method is called atomization. The next one is called chemical. And we have electrolyte. The last one is called mechanical method. And the use of mechanical method is low, but it is there, and uh, its efficiency is lower than other method that I mentioned here. Let's look at the first atomization method here in this slide. As you see, we have a siphon in this part, and we have gas, high pressure gas. We have nozzle. This part is called nozzle, and we have a collection chamber at this part. What happens? We have a high velocity gas stream that flows through that expansion nozzle, and it siphon, or this siphoning happens at that this area. So this molten metal goes up here, this part, and molten metal, when it comes there, they will be exposed to gas stream, and the gas stream spray the molten metal into a chamber, and this method um, will convert that molten metal into the spray of droplets, and the droplet solidify into powders. This method is most versatile and popular method for producing metal powders, and it is applicable to almost all metals as well as alloys. The next process is called water atomization method, and instead of gas, here we have water that will be spraying at this point. We have the molten metal located up here. Because of the gravity, this molten metal comes down, and then we have a spray of the water that will hit this molten metal, and the molten metal will rapidly be cooled and solidified, and they will be collected on the this area, the bottom part of the collection chamber. In this picture, we see the iron powder produced by water atomization technique. As you see, the size of the particles are about 50 micron. As you see, 50 micron. Some of them are 50, for example, this one, but here this one might be 100 micron. So that their size are not the same. They varied in certain range depending on the technique that was used, and also you can sort out the particles. There are two post processes in the powder metallurgy that can improve the um, part strengths. Uh, And these processes are done after the sintering step. One is called impregnation, and the other one is called infiltration. This is because we have some porosity in the powder metallurgy, and we can remove those porosity with this method. Um, First, let's look at the impact. In the impregnation, we can use oil or other fluid like a polymer that is going to be permeated into the pores of the sintered powder metallurgy part. And some of the samples um, that that uses impregnation to improve their um, performance is gears or bearings. When you have oil in the bearings or gears, so their efficiency is going to be better, higher, so they will function better. Um, Another application is when we use polymer resin into the powder metallurgy part. When the when the polymer seep into the pores in the part, what happens? It's gonna solidify. It's gonna stay there, and it will create a tight part. And next step is called infiltration, where we add or we can fill the pores in the powder metallurgy part with molten metal. So the one criteria for the infiltration is that the melting point of the filler metal must be below the melting point of pow powder metallurgy part. So, for example, if you have uh, steel or iron, they have a melting temperature of 1400 degree, 14 in for the steel. This is the degree C. You can use copper Cu for the secondary material or the filler metal to fill in the PM part, because copper has a lower melting point, which is around 1000 degree C. When we melt the copper metal and then we bring that copper metal into the PM part, we have a capillary action that draws the filler into the pores. And the result will be non-porous material. And it's called infiltrated part that has a uniform density and also improved toughness and strength.